In this video, we're going to talk about two more applications of the motion of a charged particle in a magnetic field. And then later on, we'll talk about the magnetic force acting on a current carrying conductor. So the first application that we're going to look at is the measurement of the charge to mass ratio of an electron. So this was an experiment that was performed by J.J. Thomson. So J.J. Thomson was a physicist who discovered an electron. So this is the equipment that he used. So basically you have a cathode here that is going to generate electrons, and those electrons are going to go through a region that has an electric field and a magnetic field. So because the electron has a negative charge, and if you look at the direction of this electric field here, it's pointing, this is a positive and this is a negative. So the electric force is going to be causing those electrons to move up. The magnetic force, again, if you apply the right-hand rule, the magnetic force is going to cause those electrons to move down. So if there is a balance between the electric force and the magnetic force, then the electrons are just going to keep moving on a straight line, undeflected. And then once you turn off the magnetic field, then the electrons are going to move in these deflected directions right here. So you can do two measurements. One measurement in which the electrons are moving in a straight line, and the second measurement in which there is no magnetic field, and you can see that the electrons are deflected. So using those two measurements and some equations, you can set up some equations and solve those equations to get the charge to mass ratio of an electron. Now, the second application that we're going to talk about is the application of radiation therapy. And basically this is used in the production of X-rays in the hospital. So basically this is the setup right here. So we start with the electron gun. So the electron gun is going to generate some very low energy electrons. And then those electrons are going to go through a region that has a very strong electric field. So basically the electric field is going to generate a force on the electrons and accelerate those electrons to a very high kinetic energy. So by the time the electrons are going to be at this point, the energy of the electron is very high. So notice that at this point, the electrons are still moving on a straight line. But what we need to do is that we want to direct these electrons to the target. And the only way that we can do that is to pass those electrons through a magnetic field. So again, electron moving on a straight line, it goes through a magnetic field. The magnetic field is going to cause those electrons to move in a circle. Then finally, the electrons would exit, moving in the y direction. And then finally, it's going to hit this target and generate my X-rays. So you see the picture on the right side here shows a real X-ray machine. So this is the X-ray machine. It's called the linear accelerator. It's used in the hospital for the production of X-rays. So again, it's just a combination of an accelerating waveguide. So this is used to accelerate the electrons using an electric field. And those electrons are going to go through a magnetic field to change the direction such that we can direct those electrons to the target, where they can interact with the target and generate my X-rays. All right, so now we're going to be talking about the magnetic force acting on a current carrying conductor. So basically, we can look at these examples right here. So again, if you look at a conductor, so this is a wire. We assume that this is a straight wire. We're going to place it in a magnetic field such that the magnetic field is pointing from north to south. So in the second picture, notice that the current is zero. So when the current is zero, there is no force acting on this wire. Now, when the current is going up, there is a force that is acting on the left side, so it's pushing the wire to the left. And when when the current is going down, there is a force that is pushing the wire to the right side. So I just want to mention that in this example right here, we can calculate the direction of the force using the right-hand rule. So again, if you use the right-hand rule, the current, so if you know what the direction of the current is, in this case, the magnetic field is pointing into the paper, then you can use that to calculate the direction of the force. Or if you don't want to do that, you can just use cross products. So for example, in this example right here, the current is pointing up, so it's in the J direction. The magnetic field is pointing into the board, which is in the negative K direction. So if you take a cross of J and negative K, it gives you I. And then on the right side here, because the current is coming down, so the current is in the negative J direction, the magnetic field is pointing into the paper, so it's in the negative K direction. So if you take negative J cross negative K, you get I, which is pointing to the right. All right, so now we're going to talk about an equation that we can use to calculate the magnetic force on a current carrying conductor. So again, we've already said that if you have a charged particle that has some velocity, and in the presence of a magnetic field, the charged particle is going to experience a force that is given by this equation right here. Now, in a conductor, we don't just have just one electron, but we have so many valence electrons. So basically, if you want to calculate the force, all what you need to do is that you calculate the force for one charge, and then you multiply that by the total number of charge that you have in the conductor. So again, if you look at this equation right here, so again, if you calculate, so this is the force for one charge, and then you multiply it by the total number of electrons that you have inside the conductor. So again, if you remember, we said that N is the number of valence electrons per unit volume. So if this is the number of electrons per unit volume, and you multiply it by the volume of the wire, so the volume is just the cross-sectional area times the length. So all of these would give you the number of electrons that you have in the wire. And so if you put everything together here, because the current is equals to this equation right here, if you substitute that here, you can derive this equation for the force. So the magnetic force on the conductor that carries a current I is given by this equation. It's just the cross product of the length vector and the magnetic field vector. So now let's take a look at one example right here. So suppose I want to calculate the magnetic force on a wire shown in the figure given, and we're told that we have a magnetic field that has a strength of 1.50 Teslas and the length of the wire. So again, we're looking at the length of the wire that is inside the magnetic field. So the length is 5.0 centimeters, and the current is 20.0 amps. So again, so this is the positive and this is the negative. So there is a current that flows here in this wire, and the magnitude of that current is 20.0 amps. Now, if you look at this picture, because this is the north and this is the south, it means that the magnetic field is pointing from north to south. So I can set up my systems right here. So the length vector is pointing in the I direction. My current is equal to 20.0 amps. My magnetic field is pointing in the J direction. And so when I calculate the force, if you take the cross product of I and J, you get K. You end up with a force that is 1.50 Newton pointing in the J direction. So again, when I set up my system right here, I'm saying that this, so the direction of the current is I, the direction of the magnetic field is J, and then the force is going to be pointing in the K direction. So we can also calculate the direction of the force using the right-hand rule. So in the right-hand rule here, if you place your thumb in the direction of the current, and then you place the rest of your fingers in the direction of the magnetic field, then when your palm is open, it tells me that the force is pointing in the upward direction. All right. Okay. So now, what if, so the previous example that we've seen, so in this example, we said that this equation, we can only use this equation when we have a straight wire. Now, what if you have a wire that is not straight, where it's kind of twisted like this? Then we can derive a different equation that we can use to calculate the force. So basically, if you have a wire that is not a straight wire, so we can use calculus to calculate the magnetic field. So basically, you calculate the contributions from each of these length, ds, and then you just do an integral over the entire length of the wire. So the force is just the current times the integral from point A to point B, the cross product of the length vector ds and the magnetic field vector. All right. So now let's take a look at example number 28.4. So in this example, we want to calculate the force on a semicircular conductor that is placed in the magnetic field. So we have a wire that is bent into a semicircle of radius r, and it forms a closed circuit and carries a current I. So again, if you look at the system right here, so this is my current, it's going like that. So the current is going in the counterclockwise direction, and there is a magnetic field, and the magnetic field is pointing in the y direction. So the current here is going in the x direction, and then it's going to move in this direction like this in a semicircle. And so we want to calculate the magnitude and direction of the magnetic force acting on the straight portion of the wire and on the curved portion. So I want to calculate the contribution. So what is the force on the straight section? So on this bottom straight section right here, and what is the force on this curve path? So when I start with the straight segment right here, so again, because this is, so the distance from here to here is the radius. So it means that the distance from here to here, this point is just negative r. Now, because the magnetic field is pointing up, so in the j direction, and my ds is pointing in the I direction, so when I do I cross j, I get k. So again, if you take your ds cross b, this is just going to be I, the integral from negative r to r, and then this would be b dx in the k direction. And so if you take out the k direction and you do this integral, so the integral is just going to be equals to 2ir times b k hat. So this is the force that is acting on the straight portion of the wire. So now we're going to calculate the force that acts on this curved portion of the wire. All right. Now, if I want to calculate the force that acts on the curved portion of the wire, now, the very first thing that I need to remember here is that I can use, so if you look at my ds here, so my ds is equal to r times d theta, that's the magnitude. But in terms of the unit vector, so the unit vector is pointing in this direction right here, so it's negative sine of theta in the I direction plus cosine of theta in the j direction. So this is the direction here. So if you take the cross product of these with the magnetic field, you end up with a negative k hat direction. So again, if you do this integral from 0 to pi, so you want to do all the integral from 0 here up to 180 degrees, then you get negative 2i times r times b in the k hat. So this is a very, very important result. So again, we've seen that the force on the straight portion of the wire is just equals to 2ir b k hat, and the force on the curved portion is just equals to negative 2ir b k hat. So again, if you do F1 plus F2, it's going to be equals to 0. So again, so this is important because if you have a closed loop, so a closed loop of wire that carries the current in the presence of a magnetic field, the total force is going to be equals to 0.